So I'm happy to welcome vajⱧ孤ⴆtom to tell us all about hacking quantum cryptography.
Good morning. Thanks to the organizers for this opportunity to wake you up after the good conference dinner. I certainly had to wake up to give my talk. I will tell you today how the research groups around the world are working to improve security of quantum key distribution. And there will be a hacking equipment demonstration slightly past the middle of my talk. For those watching the podcast, you can get a copy of the presentation slides at this URL. The beauty of quantum cryptography is its security model. The security of quantum cryptography is based on the laws of physics. Unlike the conventional cryptography, where the security is based on unproven mathematical assumptions, quantum cryptography starts with the laws of physics. It also starts with the model of equipment, the real equipment that Alice and Bob have, and proceeds with a mathematical derivation called the proof of security. The derivation, starting with those two assumptions, arrives at an equation for the secret key rate. In the simplest case, the equation is a function of just one parameter, the quantum bit error rate between Alice and Bob. If we want to account for some equipment imperfections in Alice and Bob, the security equation gets a little bit longer. There are additional security parameters, but again, still a few parameters. In general, this equation tells you that in a certain range of the input parameters which Alice and Bob measure, you can have a secret key at the output of the system. And if the input parameters exceed a certain value, no secret key extraction is possible. The eavesdropper Eve in the channel can do everything allowed by the laws of physics. The security model is really the beauty. But it has this assumption that the model of equipment in Alice and Bob has to be correct. All the attacks you might have heard during the last few years are based on breaking this assumption. We don't contest the laws of physics. The laws of quantum mechanics, as best as we know them, are true. But people found discrepancies between the actual equipment of Alice and Bob and the model of equipment in the security proofs. So I will show you some of the attacks today. Every secure technology in its development moves through several stages. From the initial idea of a secure technology are grown the first implementations, which are good to deploy in the real world. Can be shipped to customers, switched on, don't require a physicist to attend. Then hackers come and try to find loopholes in those initial implementations, implementation loopholes. At this stage, spectacular failures are to be expected. Hackers find a vexing problem, they break the security. The manufacturers and developers proceed with patching. The hackers hack again, the patching proceeds, and after a few patching iterations. What emerges is the second generation of a secure technology, which is now very difficult to crack. A good example of a secure technology is the RSA, public key encryption system. Everybody in this room have used it when you shopped with a credit card on the internet. This secure technology is about 30 years old at this point. During the first half of those 30 years, it was broken completely several times through the loopholes and implementations. And now it is a pretty reliable technology. Quantum cryptography has passed through the first two stages and is now at this hacking stage. People who study the security of quantum cryptography are called quantum hackers. Quantum hackers discover vulnerabilities, new discrepancies between the model and the actual devices in hardware and software. Sometimes when the hackers describe there is a vulnerability, you can in principle exploit in such and such, so the security is broken. Not everyone believes. So a couple times, the last couple years, hackers had to demonstrate complete attacks, which actually spy on the line and actually get the so-called secret key in possession of the hacker. But on the other side, quantum hackers propose countermeasures to the problems they discover, and the quantum hackers also try to incorporate the newly discovered vulnerabilities into the framework of the security proofs, which is the most general countermeasure to all hacking attacks. Meet the chief enemy of the quantum hacker, commercial quantum cryptography equipment. Here you can see it installed in a server rack. The two quantum key distribution boxes grow secret keys with two remote nodes. The secret keys produced by quantum cryptography are passed to classical encryption equipment, which encrypts all network traffic with remote nodes. At this point, I would like to digress. And since the commercial quantum cryptography has become available several years ago, around 2005, many researchers worldwide try to crack it. But this field is very young, just a few years. Let me digress for a couple minutes and show you a much more mature security field, lockpicking. See a video from the famous lockpicker, mě. And this is a high security lock, newly manufactured.
This is the mě හැ5800 E-Plex series. This is mechanically the same platform as the 5000. We're going to go through and show some of the same attacks that the 5000 is vulnerable to. First, this is the E-Plex 5800 demonstrating the same vulnerability with regard to applying shock to lift or bounce the locking plunger assembly in order to open the mechanism. Toby?
This is a high security lock. Okay, it works. Good. But this is not the only loophole. You need a hammer to break this one, but let's see a different one.
First, we'll enable the remote open function and show how to bypass the system by inserting actually a metal pick and shorting out the control pin.
So they just short out an electrical connection.
You can hit the click back and forth.
Okay. So you got the idea. Looking for vulnerabilities.
Same bypass as we demonstrated with the 5000, same platform.
Looking for vulnerabilities is a well-established practice everywhere in security, and quantum cryptography has just started. So let's move to slightly more expensive hammers and lockpicks. This is the list of attacks on quantum cryptography implementations published during the last 3 years. My apologies, I probably omitted 1 or 2 attacks, they just didn't fit on the screen. There are different attacks. You can see from this table that they target different components, mostly the single photon detector, but also phase modulator, Faraday mirror. So there are different parts of the systems which are targeted. Most of the attacks have been tested and demonstrated on actual hardware. There's just only one recent attack, which is pure theory. You can see that in at least half of the attacks, people have tested security of commercial quantum cryptography systems. And then the attacks are different. They have different performance. I have picked a few performance parameters, well, how good the attack works. But those performance parameters are not very important. What is important is that every attack in this table was not anticipated by the developers, and it breaks the security completely. Every attack breaks the security. But then, if you look into the details, how the attacks were demonstrated, you see that most people did some tests on the hardware to find out that the attack, the vulnerability is present. Most of the time, people do not go into such a trouble as constructing the full eavesdropping system and actually eavesdropping transmission on the transmission line. But there were 2 experiments last 2 years which have done exactly that, full eavesdropping. Some attacks deliver the eavesdropper 100% verbatim copy of the secret key. Some attacks deliver an almost complete copy of the key. The blue lettering means you have, in principle, you have the full key or nearly complete key, sans 1 or 2% of the secret information. But the key is delivered scrambled, or there is an additional cryptanalysis task to extract, to actually break the secret. A task of a limited complexity, but it hasn't been demonstrated. But some attacks do deliver the full key. And this means, well, this is almost as good as getting the full key, because for all those attacks, it's impossible to counteract the attack by applying an extra private simplification, because eavesdropper already has almost 100%. Some attacks allow, after insertion of Eve, keep the same key rate as seen by Alice and Bob. Some attacks do reduce the key rate, at least with the present-day technology. But to summarize, those are small differences. When I showed this slide to හැⱧ寅ᴨ, he said, no, Vadim, you must have the main point in writing. So here it is. Every single attack breaks security. And for most of those attacks in the table, the issue has not, as of today, been satisfactorily addressed. So we have a problem. Today, I don't have time to tell you about all the attacks. I will tell just about a couple of them, detector control attacks. But those attacks provide a good example, which, and I will also discuss countermeasures to those attacks. It's a good example which also reflects the status with the other attacks on QKD. So let's go and see how we can control detectors in a QKD system. In quantum cryptography, to detect single photons, you need a single photon detector. And this component has provided the eavesdroppers, or quantum hackers, a rich array of imperfections during the recent years. Several vulnerabilities in it have been discovered. All practical detectors in a QKD system are based on avalanche photodiodes. An avalanche photodiode can be used to detect single photons when the photodiode is reverse biased above its breakdown voltage. It sits there and waits for a photon, no current through the photodiode. When a single photon comes, the initial photo-generated carriers quickly multiply into a large avalanche of carriers, thousands and thousands of carriers, and a macroscopic electrical current flows through the photodiode. The socket senses this current with a certain comparator threshold on the electrical current and registers this electrical current as the arrival of a single photon. Then the electrical socket of the detector lowers the voltage below breakdown, so the avalanche stops, and after a short while rises it again above breakdown, so it's ready to detect the next photon. When the voltage at the APD is below the breakdown voltage, it is still a photodiode. It doesn't really see single photons, but it still has classical photosensitivity. So if someone applies bright illumination to the APD biased below breakdown, it will generate photocurrent, which might look just exactly like this avalanche current. And now the detector can register a click with a classical threshold on the power of the input illumination. if the eavesdropper has access to single photon detectors in such linear regime, the eavesdropper can fully control the detectors with a classical threshold and break the security completely. Let's assume for a moment, until the next slide, that the eavesdropper has access to single photon detectors in such linear regime inside the receiver Bob. So Bob has linear detectors. Assume for a moment he has ones. How will the eavesdropper proceed to attack the system and break its security, eavesdrop the key? The eavesdropper Eve uses a copy of Bob's equipment to detect all single photons on all quantum states coming from Alice. They are detected in a randomly chosen basis and result in a particular bit value in Eve's copy of Bob. Then Eve uses a copy of Alice's equipment to regenerate the state with the same basis and bit value as she has just detected. But instead of trying to regenerate a single photon, she generates a bright light state and sends it to Bob. Now Bob has two possible choices. Bob chooses the detection basis, and there are two possible choices. The detection basis chosen by Bob will be the same as the detection basis chosen by Eve, and this is depicted there. Or Bob can choose a different basis than Eve. In the first case, when Bob chooses the same basis as Eve, the bright state sent to Bob interferes inside Bob, and almost all the light power will go to just one single photon detector in Bob. In this detector, the photo-generated current exceeds the sensitivity threshold, and this detector produces a click. Same bit value, of course, as Eve has detected. In the opposite case, when Bob chooses a different detection basis, not the same basis as Eve, there is no interference. Both detectors receive half the amount of light, and the photocurrent stays below the click threshold. The detectors do not click. Now you can ask, but this is no good, because half the time Eve sends a faked state to Bob, but half the time it fails to make a click. Half of your bits are lost. Wouldn't Bob notice? But in practice, this is not a problem, because Bob, when he has normally working detectors, when there is no Eve, just Bob receives photons straight from Alice, typical detector sensitivity of Bob is between 10 and 20%. And when his detectors are under bright light control of Eve, the click probability is 50%. So we can actually improve the key generation rate. Of course, we wanted to stay the same so Alice and Bob don't notice anything wrong. So notice to ID quantique. If your system suddenly starts to produce 4 times more key, could be a sign of eavesdropping.
I don't understand. If Bob uses different bases, why don't both be different?
The question was, if Bob chooses a different basis than Eve, why don't both detectors click? Because we have assumed at the beginning of the slide that the detectors in Bob are in the linear regime, not single photon detection regime. I will show you in a moment how they can be put in the linear regime. But so he has linear, he thinks he has single photon detectors, but he doesn't. They are linear, and we attack in such setting. And then the linear detectors have a classical threshold, and when the power of the light sent to Bob is kept such that when split in half, it stays below the click threshold in both detectors. So they don't see it. Now another, yes, and after this procedure, Eve and Bob have identical bases for those photons or bits that Bob has happened to detect, and identical bit values. What follows in the protocol is classical communication between Alice and Bob. In this classical communication, the first step is sifting. Alice and Bob compare their bases. And in those cases, when Alice and Bob has happened to choose a different basis, they discard the bits. when they happen to choose the same basis Bob and Alice for those bits Bob detected, they keep the bits in the key. All this classical communication in the protocol is not encrypted. It doesn't need to be according to the security model of quantum cryptography. So Eve can listen to this communication and also do the sifting, throw away the bits which Alice and Bob threw away. After the sifting step, what remains in the keys of Alice, Eve, and Bob? For every bit remaining in the sifted key, Alice, Eve, and Bob have the same basis. And in addition, Eve and Bob have the same bit value. So Eve has a full copy, exact copy of Bob's sifted key. Then Alice and Bob proceed with the key extraction steps, error correction and privacy simplification. Eve listens and does the same operations to her copy of the sifted key. And finally, everybody, Alice, Eve, and Bob, arrive at exactly the same copy of the final secret key. So the security is completely broken. Eve does not introduce any errors. So this attack causes 0 errors. Then usually after the presentation, a few people ask, but wait, how doesn't Eve introduce errors? Eve doesn't know Alice's basis. She doesn't. So if Eve knew Alice's basis, she could detect all photons from Alice in Alice's basis, and she would introduce no errors. But this is not the case. Eve doesn't know Alice's basis. She detects on a random basis. But instead, we attack the protocol on the other end. Instead of knowing Alice's basis, Eve always knows Bob's basis. So when Bob detects, Eve knows it was on the same basis. And the security is broken just as well. You can think that Bob thinks he has a single photon detection unit, but now his actual detection unit is inside Eve, and Eve just tells Bob to repeat the same clicks as she has obtained. Now let's see how the detectors in a QKD system can be put in a linear regime. In commercial systems working at telecommunication wavelengths, the detectors are working in the gated mode. This is done to reduce noise. Most of the time, the voltage at the single photon detector at the APD is kept below breakdown. And only shortly before a photon is expected, it's risen above breakdown. So, most of the time, the APD in a gated detector is actually in the linear regime. The first thing we tried, let's apply a bright pulse a few nanoseconds after the gate and see if the detector responds deterministically. And it did. And the commercial systems we tested happily registered this click with a classical deterministic threshold as belonging to this gate. So we had a full control of the detector in this gate. But unfortunately, there was a side effect. During this application of this bright pulse, a large photocurrent flows through the APD, and some of the carriers get trapped on impurity levels. Then, during the subsequent gates, the carriers are slowly released from those impurity levels, and that can cause a random click without a photon. This is called an after pulse. So we got after pulses in the following gates. The after pulses increased the quantum bit error rate observed by Alice and Bob. So the attack had a side effect. It still worked with, we could still break the security of a commercial system in a wide range of parameters, but we tried to improve, to reduce the side effect. The first thing we tried was to move the bright pulse right at the closing edge of the gate, and there we could get control with a much weaker light with less than 100 photons, but I will tell you about this attack later to the end of the presentation. The control was imperfect. Then we wanted to eliminate all side effects completely. We wanted full control with no side effects. Then we look at the electrical socket diagram of the detector, reverse engineered at first, and we saw that the reverse bias voltage to the APD is applied from a high voltage bias supply through a resistor. Don't ask me why. The manufacturers know better. Then we applied continuous wave bright light at the APD. The continuous wave bright light caused continuous photocurrent through the APD. This continuous photocurrent flows through the resistor and causes a voltage drop at the resistor. Then the entire bias voltage diagram at the APD moves down. And now the APD, even within the gate, is not in the Geiger mode. The voltage at the APD is always below breakdown. The detector becomes blind. It doesn't give any counts. It doesn't see single photons, no dark counts, no after pulses. But just as before, it would react with a classical threshold to a bright light pulse after the gate. So I should mention that this set of attacks has been executed in collaboration with the Max Planck Institute for the Science of Light in Erlangen. Let's see how we can get a full control of the detector. And of course, this is the condition to break the security. You can see detectors in adi-quantique Clavis 2 commercial QKD system. We also tried MagicQ Technologies QKD system. They work at the same. You see 3 oscillograms. On the first oscillogram, you see gates applied to the detector. Then on the second oscillogram, you see the light we apply at the input of the optical input. We begin with shining slightly above 1 milliwatt continuous wave light, which blinds the detector. Then on top of this continuous wave light, we apply a bright light pulse at a certain power level, 647 microwatts. This peak power of the pulse never causes a click, but if we increase it slightly, it always causes a click. We have full control of the detector. This was adi-quantique. This is Lars Liedersson, our PhD student, testing detectors in MagicQ Technologies QKD system. He is Bob. No, this is Alice. This is Bob. Here are lasers and equipment to control the light we apply to Bob. Now that we have full detector control, how will we proceed to eavesdrop the key on a transmission line? Well, you can come to the manufacturer and say, I need to buy a QKD system, communication set consistent of Alice and Bob. But you don't tell what you are buying it for. They sell you, you take it apart, you use Bob, Eve's copy of Bob to detect all states from Alice. You use Eve's copy of Alice to generate the bright states and send to Bob. Of course, the basis and detection result of Eve's copy of Bob becomes the input basis and input bit of Eve's copy of Alice. In addition, you need a laser to blind the detectors in Bob and an optical amplifier to actually amplify the power of the light coming out of Alice to control the detectors in Bob. For the commercial systems, we did not build this complete scheme. Well, first, because of the expense, they're quite pricey, but primarily because the attack clearly would work on the QKD part of the system. The attack would clearly work. So we thought the better application of effort is now to work to countermeasures and see how the problem can be fixed. But in a different experiment, on a research QKD system, we have actually built this full scheme and eavesdropped the full key. On the campus of the National University of Singapore, there was an installed QKD system with Alice, Bob, 300 meters of fiber between them, entangled photon pair source in Alice. One of the entangled pairs is detected locally, the other sent through the fiber to Bob. Bob has a 4-detector passively quenched detector analyzer unit, not gated, passively quenched, but they are also blindable and controllable by bright light by using the same method. In this scheme, we actually built and inserted into the line a full, complete eavesdropper, which had a copy of Bob and then a generator in a suitcase to send the control faked states to Bob. Alice and Bob happily ran quantum key distribution through this line. They did not notice anything wrong, but Eve had a full copy of the secret key in her computer. When I say they did not notice anything wrong, he added two main parameters monitored by this research QKD system, the key generation rate and the quantum bit error rate. You see that it's the same, indistinguishably the same before eavesdropping and during eavesdropping. So, no alarm. Now will be the equipment demonstration. Here I brought from Trondheim a passively quenched detector of the same type as used in this research QKD system. And this demonstration was shown last time at the QIPC conference. Maybe some people have seen it. It worked. But that was last week. Today is a different week, so let's try something new. Just yesterday, I walked around the industry exhibit in the lobby and saw two commercial manufacturers. ID Quantique had a birthday. And Q-Tools GmbH had a brand new model of a commercial single photon detector. And the industry folks have been nice enough to loan me this detector for a demonstration. So it's called QTD detection unit. Let's see if I control this new detector using the same method. I don't know exactly what is inside this box. I know they told me that this is a passively quenched detector, so it must be controllable. What I will do now, I have this detector. It also has an integrated counter which shows the number of counts per second. You can see it big on the screen. I put the webcam, so you see the count rate per second. In addition to the detector, I have a fiber input of the detector going to two lasers in my hacking suit case. But right now the lasers are switched off, so no light. The detector is free running. It shows quite a high count rate. It's 100,000 counts per second. This is mostly the ambient light from the room lights seeping through the transparent coating or transparent jacket of the input single mode fiber. I can try to reduce the amount of this light with a black cloth. If I try to cover the input, it will see fewer photons coming. Well, I can't quite reduce them. Okay, so this is closer to the dark count rate. Still quite many photons, but I have reduced the amount of ambient photons coming through almost 10 times. Now, what I will do? I will use the lasers in the setup. First, I will use one laser to apply continuous wave light to the detector and see if it becomes blind. And then I will use another laser to apply pulses of light in addition to continuous wave light and see if the detector will produce a single click for each input pulse of light. Let's go on to the demo. First, the blinding light. I switch on the blinding laser, continuous wave light. Oh, it's blind. So, attack progress 50%. Second, let's try to apply bright pulses. I have a signal generator which produces electrical signal for the laser. And this signal generator produces, right now it produces 20,135 pulses per second. Don't ask me why not exactly 20,000, because this is an old analog signal generator, it just has a knob. So I can't dial exactly 20,000, but I have a counter which sees how many pulses. So it's now 2,021.35 per second. I connect this generator to the laser, so it shines bright pulses at the detector. And the detector happily responds and produces one output pulse for one input bright pulse. Same count rate. Wonderful. So we have broken a new model of a commercial detector. I can change the count, the pulse rate, bring it, make it close to 10,000 pulses per second. So right now it produces 10,175 pulses per second, and the detector happily responds one output pulse for one input pulse. So we have full control. Now the next thing I show, I will reduce the peak power of the bright input pulses to half the amplitude and show that the detector will stop responding to the bright pulses which have half the peak power as before. I will now gradually reduce the amplitude, slowly gradually reduce the amplitude of the input pulses. I reduce the amplitude, and you see, okay, so now the detector has less than 100% probability to respond to them, and very quickly the count rate drops as I reduce the amplitude of the input pulses. It drops to 0, and now the amplitude is 50% of what it used to be. And this is the condition for to break the security in full control, because half the power corresponds to the detector looking at the amplitude, the pulses in a conjugate basis. And we don't want clicks in the conjugate basis. I increase the power back again. The attack is fully reversible. If I remove the bright light from the detector, it instantly recovers to the original state. So now it's again normally running, single photon sensitive. So thank you very much, Henning. You can take this new model of detector. It's now in a good company. We have shown full control of 2 gated detectors in commercial systems. Beside those 2 passively quenched, we have also tested 2 other passively quenched models. We have tested an actively quenched detector model, so it would make 7 models of detectors based on APDs. They were all fully controllable with bright light. Now, when we have full control, we can break security of QKD. But what else can we do? We can fake a Bell inequality. In a standard testing setting for a Bell inequality, there is a source of entangled photons, and 2 parties have analyzed the states of those entangled photons. In this example, a passive polarization analyzer is employed with a beam splitter and 2 pairs of single photon detectors looking for conjugate polarizations. Now, if those detectors are in the Bell testing setup are controllable, then somebody can replace the source of entangled photons with a pair of faked state generators controlling fully the click outcomes in the other 2 parties with a predeterministic pattern. And then, when the parties test a Bell inequality, but are actually under a full control of a faker, they can see the violation of CH-SH inequality, the parameter S reaching the unphysical values of 4. There is a Russian military joke. A colonel comes to the class and says, at the wartime, the value of pi can reach 4 and even 5. We have the same situation here. They see unphysical violation. The maximum you can do with quantum mechanics, you get 2 square roots of 2. And we have seen Paul Kwiat demonstrating that you can actually get very close to this value. But here we simulate an unphysical PR box which produces the value of 4. Or you don't have to be exactly at 4. You can get anything between -4 and 4. You can simulate the quantum mechanics if you want. And in addition, the 2 parties testing, they see 100% detection probability. Well, very good. So if your QKD protocol relies on a bell testing, like the Arthur Eckert's QKD protocol, then you are fried. To counteract this faking, to make the faking impossible, you will have to test the bell inequality and close all the loopholes in the test. In particular, you cannot have a passive basis choice. You have to have an active basis choice with a modulator. And you have to have single photon detection efficiency quite high, 67 or 83%, whatever your favorite threshold says. And then it actually becomes impossible to fake. But as long as you have the detection loophole open, as long as you don't have the active basis choice, or you call it locality loophole, then you can an attacker can fake the bell inequality. What about, this was about applications. What about a different detector technology? A superconducting single photon detector, the next wave in the detection technology, a device based on very different technology, very different physics. But it turns out it's blindable and controllable with the bright light, surprisingly in almost the same way as APDs. The superconducting single photon detector consists of a nanowire laid out in a meander. The nanowire is biased from an external bias current supply at a current slightly below the critical current. The whole thing is cooled down to 2 to 4 Kelvin, and the nanowire is normally entirely superconducting. So there is no voltage drop across, and the bias current across the nanowire slightly less than the critical current. When a single photon comes, since this is a very small thing, the single photon hits the nanowire and temporarily creates a small normally conductive region across the nanowire. So the bias current is disrupted, and this is seen by the electronics as a voltage pulse out of the nanowire. This small normally conductive region very quickly cools down and dissipates the nanowire, because normally superconducting again, it exists only during the rise time of the pulse, and then the pulse drops and the detector is ready for the next photon. Turns out, you can blind this device by applying a sufficiently long bright light pulse. We apply a bright light pulse, and the bright light causes a formation of a longer normally conductive region in a nanowire. And when the light is switched off, by the time the light has switched off, a typical power supply or bias supply of the nanowire has adapted and applied a larger voltage across it. And then what remains with no light is a self-sustaining, self-heating, normally conductive region, which is quite large. There is no electrical signal at the output of the device, but the device no longer sees single photons. It's blind. But if you apply a shorter and brighter light pulse, you supply additional energy, so the length of the normally conductive region will vary as you apply the pulse, and the current through the device will vary, and this will register in the electronics as an electrical pulse, which can mimic a single photon response. The amplitude of the pulse depends on the peak power of this input light, so if you had a detection threshold around between those two values, you could also have a full control of the superconducting detector. And by the way, this is a simulation. This is what we think might be happening, but I can't say if the region is continuous or maybe it's spread in small pieces across the nanowire. But this is what we see at the electrical response at the output. So, a couple general notes on hacking. In the classical security community, it's an accepted good practice. When you hack a commercial device already installed to customers, it is good to notify the manufacturer, notify the developer about the discovered vulnerability, and give them a chance to react, patch, or at least alert the customers. I hope that this becomes a practice in this security community also. We have done this responsible disclosure when we hacked the 2 commercial systems. The manufacturers had detailed vulnerability reports several months before the results went public. One of them used the time to develop a countermeasure, a patch. So now you can ask, with this hacking technology, we know how to control detectors in a commercial system. So can we then go in, connect to the fibers going out of this commercial installation, and eavesdrop the full key? What do you think? Can we eavesdrop on the commercial installation? Careful silence. Well, it might be illegal, but okay. I was relieved to learn that we actually can't eavesdrop because the manufacturers at this time are smarter and they don't rely on quantum cryptography alone. They have quantum key distribution in this commercial installation. But they also have a classical key distribution using RSA cipher. They take the two keys, one distributed by quantum means, the other distributed by classical means. They XOR them together. And then this master key is used in a symmetric cipher to encrypt all network traffic. In order to break the security, to get this master key, we will have to break both QKD and the best classical key distribution technology at the same time. The classical we haven't done. So, and by the way, this classical part of key distribution is fully certified commercial encryption equipment. You can buy it without QKD. I think, nevertheless, such a combined system with an extra layer of security is a very good investment, even today as we try to hack QKD. Because with this dual key distribution, you are never worse than just with classical, because the security of this master key is at least as strong as the strongest of the two keys. So when we hack QKD, the security still protected by classical technology. The manufacturers now patch QKD, and if somebody in the future cracks the classical key distribution technology, the security will be protected by QKD. The chances that you are hacked are much less than if you only use the classical encryption technology, because there are two different, very different encryption key distribution technologies, and it's difficult to crack them at the same time. So, good value, I think. But to make it even better value, we now have to work to patch the loopholes in the QKD as best as we can. So now what we can do about the countermeasures? I think at this point everybody agrees that hacking is good. There is no option not to hack, and all people around encourage our activity. So what about the real countermeasures that can be applied to such equipment loopholes? There are two different kinds of countermeasures. The first kind of countermeasure are so-called quick and intuitive patches. All the attacks, or most of the attacks demonstrated, that use implementation loopholes. They have side effects. There is too much light coming, or too much current through the circuit when the attack is applied, or something else, the timing is wrong. So they have signatures of the attack inside the device. Those parameters are usually not monitored in QKD. They are not considered a security parameter. But we can modify the device, we can modify the protocol to include this monitoring for the extra security, make them extra security parameters and monitor. And when they exceed the normal values, we raise an alarm and send two security persons with a dog and Kalashnikov rifle down the line to find Eve. I have two problems with this intuitive approach. The first major objection I have, and the other one is minor. The major objection is that when you start monitoring those extra side effects and place alarms on them, this is outside the model of the security proof of quantum cryptography. Before, you had security relying on the security proof which starts with the laws of physics. So you rely on the laws of physics alone. And now, after applying such an intuitive countermeasure, additional countermeasure, you rely on the security proof, and in addition to that, you also rely on the assumption that the countermeasure you have applied will work in all situations. What if you have missed something? This is an unproven assumption that the countermeasure will work. The same as in classical cryptography, which also relies on unproven assumptions, you now also rely on an unproven assumption. Why would anybody bother to do QKD if you reduce the security model of QKD to the same as classical cryptography? You rely on unproven assumptions. I think this is not good. And the minor objection is that actually improved hacking technology can break your initial countermeasure. I think this might have happened when Liedersson demonstrated the superlinearity of single photon detectors, which might just be the attack which might go around the set of technical countermeasures proposed by the group in Toshiba. An alternative approach is to integrate the loophole in the security proof, in the framework of the security proof. Make it a part of the security proof. This might be difficult. You might have to modify the equipment, the protocol, and the security proof. But we have a successful example how this approach was applied to multi-photon components of the source. When you use a laser, weak coherent pulses, sometimes you have more than one photon in the line. The decoy state protocol is just such a deep modification of the protocol, hardware, and the security proof, and it works beautifully. It has completely closed the security loophole. For the detector control loophole, there have been attempts to close this vulnerability. Our group has worked. This is recent, just of last week, posted preprint by හැ₧kwon close group, which proposes a completely new key distribution protocol, which just takes away the detector's U. The detectors are untrusted in this protocol, just given to Eve. I will not comment on this work because it's quite new and I'm not the right person to, but I will go quickly through our security proposal, how to integrate. So I will now brief you quickly on the progress of those two types of countermeasures, the technical and integration and security proof, for the case of detector control loophole. This is the countermeasure proposed by the group in Toshiba, Yuan, Dines, Shields. They have looked at the electrical signals in the standard gated detector with bias, gate applied at the APD, and at the output of the detector. When there are no photon counts, they see such an up and down pulse shape, which is just the gate signal getting differentiated, seeping through the capacitance of the APD. When there is an avalanche, then in addition to this up and down shape, you have the avalanche signal, which is higher. So you can place a comparator threshold in between those two levels and register an avalanche. Then they applied continuous wave blinding light to this APD and found out that if there is no bias resistor, the bias resistor is 0, it's shorted out. Actually, they originally had in their design no bias resistor. Then under continuous wave elimination, the voltage at the APD does not drop very much. It is around the breakdown voltage. So the application of the gate to the APD changes the voltage there and changes the gain of the APD in respect to the bright input continuous wave light. Then you see a larger pulse at the output of the socket. And Eve tries to blind the APD. She cannot blind. There will be a click in every gate. So she can't blind the APD. Then the proposed set of countermeasures by this group is summarized here. You have to have the bias resistor at 0. You have to set the comparator threshold properly, just above the capacitive signal, not much higher. In addition, you have to monitor the, the Eve can be smarter. She doesn't have to blind with continuous wave light. She can, for example, just switch off the blinding light just before the gate and switch it on again after. So there will be no pulse, but it will still cause excessive current consumption from the bias source. So monitor the bias current for anomalously high values. And the fourth countermeasure is that you only have to accept the clicks in the narrow time slot, narrow time window about the same width as the gate. This is to prevent the after-gate attack when if applies bright pulses after the gate. I have a couple problems with the set of countermeasures. The first one, just how high is too high? This condition to monitor the current and raise alarm when it becomes too high is not a part of the security proof. Ideally, this threshold should be derived from the security proof and fed in the QKD protocol, but it's not. It stands outside, so there is no guarantee it is a part of the security model. And second, with these narrow acceptance windows, real clicks at the detector have jitter. You have a photon coming at a certain time, but the avalanche can register, the crossing of the comparator threshold can register with a certain time distribution. So there is no guarantee a narrow acceptance window will be insensitive to photons falling outside it. And indeed, we have done tests on a gated detector in Clavis 2 commercial QKD system. We try to see what is the single photon sensitivity of the detector as we scan a narrow light pulse, 200 picosecond light pulse, in time across the gate. We take this narrow pulse and scan the sensitivity across the gate. The first, we attenuated this narrow pulse to a single photon level, to be about 1 photon per pulse, and measured the sensitivity. And then we model what happens when the number of photons per pulse is increased to 20, 40, 60, and 80 photons per pulse, assuming that each of those multiple photons is detected independently in the detector. So the probabilities add up to the total detection probability independently based on the measured single photon sensitivity. And this is the green sensitivity curve, the theoretical calculation, assuming independent detection of multiple photons. The red curve is the actual measured sensitivity at this photon number, and you see that it is different at the closing edge of the gate. It is higher. As the photon number is increased, the difference gets larger and larger and larger. So somehow photons coming together help each other and have a higher probability to cause a detection than if they just come individually. If you take a time at 4 nanoseconds and plot the sensitivity curve of the detector, this is what you would expect in the individual detection model, and this is the actual detection probability. You see that it has this skiing jump slope. So can you exploit this superlinearity of the detector? Say if you send a 50 photon pulse, and in the attack shown previously, a 25 photon pulse would cause no clicks. In this attack, it still causes quite many clicks, so the quantum bit error rate will be non-zero. But we modeled an intercept-resent attack with such relatively dim pulses, and we have got a quantum bit error rate between 12 and 14%, which is quite high. It's above the 11%, which is the standard threshold for the QKD. But an intercept-resent attack should cause 25% errors. And it causes between 12 and 14, half that much. So it sort of works. There is an advanced QKD protocol which works up to 20% errors. That protocol will be definitely broken by this attack. In addition, we think we didn't quite have very narrow light pulse. We only had 200 picosecond. If we use a narrower light pulse, maybe the discrepancy can be improved. And this is only one detector model tested. And in this attack, Eve applies quite dim pulses, just several tens of photons. So no increase of current. It will look just like a single photon pulse. And it is quite close to the closing edge, so no detection window might miss this attack. The timing will be almost the same as the normal single photon detection. So this is a graphic example how the set of intuitive countermeasures can be broken, might be broken. On the side of integrating in the security proof, our group has been working with this is you. We have actually produced a security proof which integrates arbitrary individual detector imperfections as a single parameter in the equation for the secure key rate. The problem was how to get a practical estimate of this detector parameter. In the initial security proof, this should be the detector sensitivity anywhere on the timeline. And it can be quite low outside the gate, and then if you plug the sensitivity outside the gate in the security proof, it produces 0 secret key rate. No good. So we come up with an addition, a modification to the protocol we call bit-mapped gating. The idea is that BOP applies random basis choice outside the gate, and only in a narrow time slot in the middle of the gate, the actual basis choice is applied. Then we show that only in this time region, it's enough to quantify the detector sensitivity only in this narrow time region. And when you quantify, you can plug this number, which is now much higher, into this security proof and actually get non-zero key rate. You still have to guarantee single photon sensitivity. So we think maybe there should be a hardware addition, a small calibrated light source inside BOP, which is activated at random times and tests the detectors in BOP for single photon sensitivity. You see correlations between the activation of this calibrated source and the clicks in detector in BOP, you might guarantee the single photon sensitivity. But this is work in progress. It has not been finished. No hardware demonstration has been done. So we have those two alternative approaches. And I have shown the examples for the detector control attack, but this situation is also the situation for the other attacks made in recent years. So this is an accurate reflection. They also have two different approaches, technical countermeasures or try to integrate in the security proof. Which approach will win? I prefer, of course, the general countermeasure integration in the security model. But I don't know. Maybe there will be a synergy of the two approaches or something else completely. I don't know. Time will tell.
Thank you.
Thank you. Thank you for attention. I have a short announce. I'm moving to Institute for Quantum Computing, Waterloo, Canada, early next year, and I have open PhD positions. So if you're interested, come and talk with me. Thank you.
Okay. Okay, so actually, if we could have the next speaker come up while we take questions.
Thank you. At some point you said that you could not break the current ED quantic commercial system, Cerberus, because for that, and I quote you, to break it, you would need to break both the quantum key distribution and RSA at the same time, you said. I must disagree. You have to break the quantum key distribution while the protocol is going on, and then you can store everything that you can just store everything that you recorded and break RSA later.
Let me see. Maybe, but they actually, in the QKD system, they actually encrypt key extraction exchange in a VPN channel, which is also relies on RSA in classical ciphers. But yes, maybe you are right.
I mean, if there is some synergy between the RSA and the quantum key, perhaps. But if we describe it as being two separate things, no. You can break.
Yes, in principle, we can break the quantum part and then wait until we have technology to break the classical part. In principle, yes.
Thank you.
Other questions?
I have a comment about the last point about the two kinds of countermeasures. And I would suggest that I think what will happen is that we'll have both going on, the integration into the security proof being more on the research side and the patches being more on the practical side. Because I think what you're showing is that it's a mistake to take some kind of cryptography directly out of the research world and use it directly in the practical world. Because these research systems tend to be very brittle in their security. You have a single point of failure. Whereas in practice, you want some defense in depth, some situational awareness, and these are very practical things that I think need to be developed for this to become a real practical technology. Whereas for the research, I think the right-hand side is going to be a very important and very interesting thing for us researchers.
I agree, but I might add that you should limit the number of security measures. You can't make infinite number of security measures.
Okay, last two questions.
So it would seem that one advantage of your system is that you don't have to shield the fiber against ambient light.
Yes. No, it's open, and we can still blind it. See. Yes, when it's blind, it doesn't see ambient photon, 0. No, yes, it is an advantage.
So, may I ask?
Yes.
Could you comment on the a kind of loophole, not only on the QKD devices, but just above the QKD system, like layer 2 switches or L2 VPN? Maybe your assumption is that you can be just near the Alice, so you can access to any kind of switches, even including layer 2 switches.
We can't access inside. The transmission line is classical. It's electrical line, and an electrical line is much easier to isolate from the secure content. So even if you put 1,000 volts in, I think all will result as a burnt-out buffer. So the isolation is much easier in the. This is why the attacks which access through the transmission line are not seriously considered in classical cryptography. Isolation is easier, but the security loopholes, implementation loopholes, can exist, of course, in quantum cryptography and in classical cryptography alike. So the situation is not different. In classical and quantum cryptography, both can have implementation loopholes. You need to search for them. There is never a guarantee you haven't missed a loophole, both classical and quantum. What is different is the foundation of the technology. For a classical cryptography, you base on unproven assumptions. For the quantum cryptography, you base on the laws of physics and principle. So for classical cryptography, also the foundation can be broken. For quantum, only the implementation loopholes matter.
Okay, let's push other questions to the coffee break and thank vaj once again. Thank you.